Welcome back everyone. We are now moving into Unit 5 and the first topic we will be exploring is vibration measuring devices. This is a crucial area in vibration and noise control, as understanding and quantifying vibration is the first step towards effectively controlling it. I am Dr. C. Sendamarekannan, Associate Professor in the Department of Mechanical Engineering at SVC. Feel free to reach out if you have any questions regarding this topic or any other material we can cover in this course. ME22088 Vibration and Noise Control. In the subsequent sections, we will delve deeper into different types of vibration measuring devices, their working principles, and their specific application. So stay tuned. Alright, now that we have an introduction to one fundamental type of vibration measuring device, let's take a look at overall syllabus for Unit 5. As you can see, the Unit 5 comprises of measurements and control of vibration. We will start exploring by vibration measuring devices in more detail. This includes understanding different types of transducers and vibration pickups. Beyond the piezoelectric accelerometer, we just using day-to-day applications. We will look at the specific characteristics, how they work, and when to choose one over the other. Next, we will move on to vibration exciters. To study and analyze the vibrational behavior of systems, we often need to introduce controlled vibrations. We will examine different methods for doing this, including mechanical and hydraulic exciters. Understanding how this work is crucial for experimental vibrational analysis. Following that, we will discuss frequency measuring instruments. This section will cover tools like single read, multi-read, as well as the stroboscopes. These instruments are essential for determining the frequencies presenting in a vibrating system. We will then delve into experimental modal analysis, and in particular we will focus on FFT analysis. The fast Fourier transform FFT is a powerful tool that allows us to decompose complex vibration signals into their constituent frequencies, providing valuable insights into the system's dynamic characteristics. Further, the unit will conclude with vibration control methods and devices. Here we will explore various techniques and devices used to mitigate unwanted vibrations. This include isolators, observers, which are designed to dampen vibrations at specific frequencies, and some balancing techniques which are crucial for rotating machineries. And then we are seeing the course outcome, that is, for this unit, what will be the course outcome? That is, by the end of this unit, you are able to do some suitable methodologies for measuring and controlling the motions of mechanical systems. This means you will gain the knowledge and understanding to select the appropriate tools and techniques for both analyzing and mitigating vibration problems in various engineering applications. So, as you see, Unit 5 provides a comprehensive overview of both how we can measure and how we can control vibrations. We will build upon the concepts what we have already started and exploring as a range of practical and theoretical aspects in the forthcoming lectures. Here in this slide, I am just giving outline for our topic vibration measuring devices, specifically we will be focusing on transducers. So initially there will be a brief introduction to vibration measurement and the role of transducers within that process, and also there will be importance of how to quantify the vibration and setting the stage for understanding different types of devices that we are going to discuss. This section on transducers will likely to cover different categories and types, expanding on the piezoelectric example also, and variable capacitances, inductive transducers, strain gauges, etc. So this lecture will lay the groundwork for understanding the various tools we use to sense and measure vibrations. Let's address a fundamental question. Why is it so important for us to measure vibration? Which is, measuring vibration allows us to detect shift in the natural frequencies denoted as omega n, which can be a critical indicator for potential failures in the machineries or structures. The change in natural frequency often signals a change in the system's physical properties such as loosening components, cracks or wear, which could lead to catastrophic failure if left unaddressed. Secondly, vibration measurements are essential to select operational speeds that avoid the resonance. As we discussed previously, resonance occurs when the excitation frequency is equal to the natural frequency of the system, which will lead to large and potentially damaging amplitude of vibrations. So, by measuring the natural frequencies, we can operate equipment at speeds that are far from these critical speeds. Third, we are going to see that how this measured vibration values may often differ significantly from theoretical values. Our mathematical models are simplifications of reality. Factors like manufacturing tolerances, material inconsistencies, and complex boundary conditions can lead to actual vibrational behavior that deviates from our predictions. Experimental measurements provide real-world data we need for accurate analysis and design purpose. Fourthly, understanding and measuring existing vibration is crucial to design active vibration isolation systems also. These systems use sensors, actuators to actively counteract unwanted vibrations. Fifthly, we are going to see the vibration measurements, how to be used to identify key system parameters like mass, stiffness, and damping. By analyzing this vibrational response of a system to known input, we can experimentally determine these fundamental properties which are vital for accurate modeling and prediction of future behavior. Building upon our understanding of why we measure vibrations, the next logical question is, how do we choose the right instrument for the job? Here, I am highlighting several key factors that will tell how to choose the measuring instrument. Firstly, the expected range of frequencies and amplitudes, which is very much critical consideration. Different transducers and instruments have varying sensitivities and operating ranges. For instance, some transducers are better suits for measuring high frequency but low amplitudes, while others excel at capturing low frequency, high amplitude movements. we need to select an instrument that can accurately capture the entire spectrum of vibrations we are anticipating. Second, the size of the machine or structure involved can influence our choice. For very large structures, we might need robust and potentially more spatially distributed sensor networks. Conversely, for small or intricate mechanism, we might require miniature and lightweight transducers to avoid significant system dynamics, which will be affected when we are using some miniature transducers. Accessibility for sensor placement also very much important factor related to size and geometry of the transducers. The third condition is operation of the machine or structures, which is significant, very much significant factor, like temperatures, extreme humidities, presence of corrosive substances, or even high level of electromagnetic interference can necessitate the use of specialized transducers and instruments that are designed to withstand these challenging environments. For example, an accelerometer used in an aircraft engine will have very different requirement than one used in a laboratory setting. Finally, type of data processing used can also influence the selection of measuring instruments. Some transducers provide a raw voltage signal that requires significant post-processing, while others might have built-in signal conditionings. The compatibility of the transducer's output with our data acquisition system and analysis software is an important practical consideration. Therefore, when faced with a vibration measurement task, it's crucial to carefully consider these factors: the expected vibration characteristics, the physical aspect of the system, the operational environment, and the intended data analysis methods to ensure that we select the most appropriate and effective vibration measuring instruments for obtaining accurate and meaningful results. We will now move on to explore different types of transducers in more detail, keeping these selection criteria in mind. Let's focus specifically on transducers. As we have alluded to, a transducer in the realm of measurement is essentially a device that transforms values of physical variables into electrical signals. Think with respect to our block diagram, the vibration transducer or pickup is the crucial link between mechanical motion of a vibrating structure, a physical variable, and convert into an electrical signal that our instruments can then be processed and display and analyze. This conversion is the fundamental role of any transducers. In the context of vibration measurement, these physical variables could be displacement, velocity, acceleration, or force. Transducers design and operating principle determines which of these quantities is primarily sensitive to and how it converts mechanical input into a corresponding electrical output, typically a voltage or current. Second thing is, we are going to see some important transducers specifically used for measuring vibrations. This means we will now move on to explore different types of transducers, each with its own unique mechanism for converting mechanical vibration into electrical signals. Now we will begin looking at specific types of vibration transducers. First category is variable resistance transducers. The fundamental principle behind this transducer is the mechanical motion causes a change in the electrical resistance, which in turn leads to a change in voltage or current in a circuit. They are part of it. By measuring this change in electrical properties, we can infer the magnitude of the mechanical displacement, strain, or acceleration that caused it. A common and important example of a variable resistance transducer, particularly relevant in vibration and structural analysis, is the strain gauge. A strain gauge is essentially a fine wire, which is bonded to the surface where strain is to be measured. See the diagram. The figure A shows a typical planar configuration of a strain gauge. You can also see a fine wire, often made of an alloy like advance, arranged in a grid-like pattern, bonded to a backing material, is often a thin paper or flexible polymer. Electrical leads are attached to the end of this fine wire. When the surface to which the strain gauge is bonded experiences strain, measuring it is either stretched or compressed. Fine wire within the gauge also experiences a change in its length or cross-sectional area. Further, this figure B clearly showing the cross-section along the line XX in the figure A. You can see the fine wire embedded within a cement or adhesive layer, which ensures good bonding to the thin paper backing. The key principle here is that when the fine wire is stretched, its length increases and its cross-sectional area decreases, both of which causes electrical resistance to increase. Conversely, when the wire is compressed, its length decreases and its cross-sectional area increases, leading to a decrease in resistance. By precisely measuring the change in resistance of this strain gauge and knowing its gauge factor, a property that relates to change in resistance to the applied strain, we can able to accurately determine strain experienced by the surface it's bonded to. In vibration analysis, strain gauges can be used to measure the dynamic strain in vibrating structures, which can then be related to stress and overall vibrational behavior. While strain gauges themselves primarily measure strain, they can be incorporated into other transducer designs to measure quantities like force, pressure, and acceleration. By relating these quantities to the strain, they induce in a sensing element. So, variable resistance transducers, particularly strain gauges, offer a direct way to sense mechanical deformation and are a valuable tool in understanding the dynamic behavior of a vibrating system. Continuing our discussion on variable resistance transducers, specifically strain gauges. The fundamental relationship that allows us to quantify strain through resistance measurements only. The first key point here is the surface to which the strain gauge is bonded and the fine wire within the gauge both undergo the same strain. This is the crucial assumption that allows us to infer the strain in the structure from the change in the wire's resistance. When the surface is stretched or compressed, a wire experiences same proportional length in length. That is, same proportional change with respect to the length changes. The slide then we are going to see in this, there is an equation that relates the change in resistance of the wire to the applied strain let me see what is the K is. Gauge factor of the wire. This is a crucial property of the strain gauge material. It is essentially tell us how sensitive the resistance change is to the applied strain. Higher gauge factor means larger change in resistance for a given strain, making the measurement more sensitive. R is the initial resistance of the unstrained wire. Del R is the change in resistance of the wire due to the applied strain. This is the quantity we measure. L is the initial length of the wire. Del L is the change in length of the wire due to the applied strain. The ratio del L by L represents axial strain. Nu is Poisson ratio of the wire material. Poisson ratio describes the tendency of a material to contract in width when stretched and expand in width when compressed. This change in cross-sectional area allows to change in resistance. Then rho, resistivity of the wire material. The resistivity is a measure of how strongly a material opposes the flow of current. Then there is going to be del R, which is change in resistivity of the wire due to the applied strain. This equation shows the gauge factor K is approximately equivalent to 1 plus 2 nu. Particularly for material like advance, where the change in resistivity of the wire is approximately 0. This simplification makes the relationship between change in resistance and the strain more direct, primarily dependent on the Poisson ratio of the material itself and the geometric changes caused by the strain. In essence, by measuring the change in resistance del R of a strain gauge with a known initial resistance R and a gauge factor, we can accurately determine the strain experienced by the surface to which it is bonded. This ability to quantify the strain makes strain gauges are invaluable tools in experimental analysis, and indirectly we are understanding the vibrational behavior of the structures. Continuing our discussion of variable resistance transducers, here this slide we are going to see that how strain gauges can be utilized in a practical vibrational pickup setup. Here we see that is the fundamental relationship we discussed earlier, now rearranged to directly solve for strain, that is del L by L equal to change in resistance divided by resistance, initial resistance, into the K, that is gauge factor. Now let me move on to this figure. A mass denoted A by M attached to a cantilever beam. This entire assembly is mounted on a base which is subjected to vibration, represented by a vertical double-headed arrow. We can see it here. Okay. Then the movement x of t indicating a time varying displacement. A strain gauge is bonded to the surface of the cantilever beam, typically near the fixed end, where the bending stress due to the mass inertia are highest. When the base vibrates, the mass due to its inertia will tend to lag behind the motion of the base. This relative motion causes the cantilever beam to bend. As the cantilever beam bends, the strain gauge bonded to its surface will experience either tension or compression depending on the direction of bending. This strain, as we learned, will cause a change in the resistance of the strain gauge. By measuring the change in resistance and knowing the properties of the strain gauge and the cantilever beam, we can infer the magnitude of the strain in the beam. This strain is directly related to the bending moment exerted by the cantilever beam which in turn related to the inertial force of the mass. Therefore, this setup demonstrates how a strain gauge, a transducer that directly measures strain, the vibrating base causes the mass to exert a force on the cantilever beam leading to the strain, which is then sensed by the strain gauge and converted into an electrical signal proportional to the acceleration or velocity, whichever the thing we are going to measure. This is the common principle behind many types of accelerometers that utilize strain sensitive elements. We understood in the previous slide how strain in a strain gauge leads to change in resistance. The next important step is how we accurately measure this often very small change in resistance del R. Here we are introducing the Wheatstone bridge for this purpose. Del R can be measured using a Wheatstone bridge. The circuit diagram on this is illustrating a typical Wheatstone bridge configuration. It consists of 4 resistors R1, R2, R3, R4 connected in a diamond shape forming 4 arms of a bridge. A voltage source V is applied across 2 opposite junctions. The output voltage E is measured across other 2 opposite junctions. In a typical application with a strain gauge, one or more of these resistors in the bridge would be the strain gauge itself. That is, from here we are connecting to the strain gauge. When the strain gauge resistance changes here due to an applied strain, it causes imbalance in this Wheatstone bridge. The equation shows here the relationship between the output voltage and the resistance of the 4 arm of the bridge. This equation shows the output voltage E may be 0 when the bridge is completely balanced, that is R1, R3 equal to R2, R4. That is, the numerator should be equal. This one of the resistors, say R1, changes its resistance due to strain. This balance condition is no longer met and a non-zero input voltage is produced. So, by carefully measuring this output voltage E and knowing the initial resistance of the bridge components and the gauge factor of the strain gauge, we can preciously determine the change in resistance del R and consequently the strain experienced by the gauge. The Wheatstone bridge configuration offers several advantages for strain gauge measurements. It provides high sensitivity to small change in resistance and can also help in compensating for temperature effects if multiple strain gauges are used in the bridge circuit in specific configurations. This makes the Wheatstone bridge an indispensable tool for accurately measuring the output of variable resistance transducers like strain gauges in vibrations and other mechanical measurements. Let we continue the discussion on the Wheatstone bridge, that is for measuring changes in resistance. Let me recall, that is, initially resistance in the Wheatstone bridge are adjusted so that the output voltage E is equal to 0. It is the initial condition. The condition for that balance state is given by R1, R3 equal to R2, R4. When this condition is met, the potential at point B and D in previous circuit diagram are equal and therefore no voltage difference across these points. That is E equal to 0. Let's consider what happens when one or more of the resistance denoted as Ri changes by a small amount del Ri due to an external factors. This change in resistance will cause the bridge to become unbalanced and a non-zero output voltage will appear across B and D. This is the approximate expression for the output voltage, where V is the input voltage to the bridge. R0 is a factor related to initial configuration of the bridge, which is given here. This equation del E is very crucial. It shows that the change in output voltage is directly proportional to the input voltage and the fractional changes in the individual resistance of the bridge arms. The sign in the equation indicates how a change in each resistor affects the output voltage. Let's consider a specific and common way in which a strain gauge is implemented in a Wheatstone bridge. If the lead are connected between point A and B, refer our Wheatstone bridge diagram, then in this case let assume R1 is our active strain gauge with an initial resistance Rg and a change in resistance del Rg due to applied strain, and also other change in resistances R2, R3, R4. Del denotes changes. Okay, other three resistors in the bridge are fixed and don't change the resistance. That's why we are putting it as 0. Under these conditions, the equation relating the fractional change in resistance to the output voltage simplifies significantly. This is the formula for the simplified arrangement of this, where this Rg is the initial resistance of the gauge, then Vr relates the fractional change to the change in output voltage del E, input voltage is V, that the bridge configuration is going to be given as R0, that is small R0, this one, where epsilon is the strain experienced by the gauge del L by L, K is the gauge factor of the strain gauge. So from these equations, we can see a direct proportionality between the change in output voltage del E and the strain epsilon. Specifically, del E is equal to the gauge factor K multiplied by the input voltage, bridge factor and strain. Hence, E can be calibrated to read strain directly. This is the key advantage of using a Wheatstone bridge with a strain gauge, because the output voltage del E is linearly related to the strain E. We can calibrate the measuring instrument connected to the output of the Wheatstone bridge directly to display the strain value itself. This calibration will be taken into account the gauge factor K and input voltage V and bridge configuration factor R0. So, I concluding that this Wheatstone bridge, through that we can use the strain gauge, which is a most powerful tool for strain measurement in various applications, including vibration analysis, where dynamic strains are of greater interest. Now let's shift our focus to another important type of vibration transducer, piezoelectric transducers. The fundamental principle of piezoelectric transducer is certain materials can generate electrical charge when they are subjected to mechanical deformation or stress. This direct conversion of mechanical energy to electrical energy is the basis of how these transducers are working. And this is the formula which is going to give you how the charge is generated due to the force, where Q of X represents electrical charge generated by the piezoelectric material in a particular directions. Direction since here it is X direction, that's why that is Q suffix X. K is the piezoelectric constant of the material. This constant is a material property that defines the amount of charge generated per unit of applied force or pressure. Different piezoelectric materials have different piezoelectric constants which dictates their sensitivity. Then f of x, a force applied to the piezoelectric material in x direction. A is the area on which the force F suffix x acts. P of x is the pressure due to the force F of x, which is nothing but P of x equal to F divided by A. Therefore, the equation shows the generated charge is proportional to the applied pressure and the area. In essence, when the piezoelectric material is compressed or stretched or subjected to shear force, it produces an electrical charge that is proportional to the magnitude of applied force or pressure. This generated charge can then be measured as a voltage across the material, providing an electrical signal that is directly related to the mechanical input. Piezoelectric transducers are widely used in vibration measurement, particularly for accelerometers, because they provide a direct and rapid response to change in accelerations, which translates to a force on a piezoelectric element due to the inertia of a mass. In this slide, we are going to see the construction principle of the piezoelectric crystal. Before that, let me just recall the previous formula, that is equation. The voltage, output voltage, is going to be equal to V, voltage sensitivity, T, thickness of the crystal, and P of x is pressure due to force F of x. If I want to find out the force, it is to be area into pressure. So, this equation highlights the output voltage is directly proportional to the applied pressure and thickness of the piezoelectric element as well as material voltage sensitivity. The schematic diagram we can see here, it is a piezoelectric accelerometer. Let's see the components. We have a base that is subjected to vibration. Resting on this base are piezoelectric disc. Above the piezoelectric disc is a mass, and this mass is often preloaded against the piezoelectric disc by a spring. Leads are connected to the piezoelectric disc to carry the electric signal. When the base of the accelerometer is going to be vibrate, the mass due to its inertia exerts a force on the piezoelectric disc. The initial force is proportional to the mass into acceleration. We very well know this force acting over the area of the piezoelectric disc create a pressure, that is our P of x. This pressure on the piezoelectric disc generates an output voltage. Since the force is proportional to the acceleration, resulting output voltage from a piezoelectric accelerometer is proportional to the acceleration itself of the vibrating body to which the base is attached. Therefore, by measuring the output voltage from a piezoelectric accelerometer, we can directly determine magnitude of acceleration of the vibration. This direct relationship, along with their high sensitivity and wide frequency range, makes piezoelectric accelerometers are one of the most commonly used transducers for measuring the vibrations. To solidify our understanding how piezoelectric transducers are working, let's look at an example problem where this problem states a quartz crystal having a thickness of 2.5 mm is subjected to a pressure of 50 psi. That is, we have to find out output voltage if the voltage sensitivity is 0.055 volt per meter Newton. So thickness of the quartz crystal is T equal to 2.5 mm. We will convert this into meter so that it is T equal to 0.00254. Applied pressure is P of X, it is 50 psi. We need to convert this into Pascal to match the unit of voltage sensitivity. So 1 psi is approximately equal to 6894.76 pascals. Therefore, P of X equal to 50 into 6894.76. Hence, the pressure is 344738 that we can substitute here. Voltage is directly given in the question 0.055. So, while substituting, just multiplying in the calculator, we are getting the value, that is the output voltage is 47.401 volt. Therefore, a quartz crystal of thickness 2.5 mm subjected to a pressure of 50 psi having a voltage sensitivity of 0.055 volt meter per Newton. The output voltage generated by the piezoelectric transducer is approximately 47.4 volts. This example demonstrates how the output voltage is directly proportional to the voltage sensitivity of the material, its thickness and the applied pressures. Let's explore another important class of vibration transducers. It is electrodynamic transducers. This device operates on the principle of electromagnetic induction, a fundamental concept in physics. The key idea behind electrodynamic transducers is that a voltage E is generated when a conductor, typically a coil of wire, moves with a magnetic field as illustrated in this diagram. This is based on Faraday's law of induction, which states that changing the magnetic flux through a circuit induces an EMF, that is electromotive force or voltage will be induced. In this case, movement of this coil through the magnetic field causes change in the magnetic flux linking the coil, thereby generating the voltage. The fundamental equation is D into L into V, where E is the generated voltage, D represents magnetic flux density. Magnetic flux density is a measure of strength of the magnetic field. L is the length of the conductor that is moving within the magnetic field, and it is perpendicular to the field lines. The case of a coil with N turns, I would effectively be N times the length of wire segment cutting the flux lines. So, the velocity is the conductor related to the magnetic field, that is represented as V. Greater the relative velocity, greater the change in magnetic flux. Thus, the larger induced voltage eventually, that is E. So, this diagram here we can see that very much how these electrodynamic shakers are working. Once again I am repeating it. It consists of a coil of wire suspended by a spring within the magnetic field created by permanent magnet, very important. When the base of the transducer vibrates, coil move related to the stationary magnetic field. This relative motion induces a voltage in the coil. Magnitude of this voltage is proportional to the velocity of the coil movement. Therefore, electrodynamic transducers are primarily velocity sensitives. They are commonly used to measure velocity component of vibration. By integrating the velocity signal with respect to time, we can obtain the displacement, and by differentiating it with respect to time, we can obtain the accelerations also. So these transducers are often found in seismographs and vibration monitoring systems where velocity information is directly very much valuable. At last, let's discuss another important type of transducer used for measuring the vibration, particularly displacement. We are going to measure it, that is because of linear variable differential transducer. It is a type of transformer. As the thing is very important, the output voltage of an LVDT depends on the axial displacement of the core. This makes it primarily a displacement transducer. The second thing is, the key advantage of LVDT is they are generally insensitive to temperature vibrations and provide a high output voltage, which can simplify the signal processing. This is the construction diagram of LVDT. It consists of 3 coils, a primary coil located in the center, 2 secondary coils positioned symmetrically on either side of the primary coil. These coils are wound around a hollow cylindrical formers. This is that is core. A movable ferromagnetic core slides axially within this former. When an AC voltage applied to the primary coil, it produces an alternating magnetic flux. This flux inks with secondary coils, inducing AC voltages in them. Let's call the voltage induced in the first secondary coil and voltage induced in the second secondary coil. When the core is centrally located at null position, the magnetic flux linking both secondary coil is equal, and if the secondary coil is wound with the same number of turns, that is connected with the series in opposition, their output voltages will be equal in magnitude and opposite in phase, resulting in net output voltage. However, the core is displaced axially from this central null position. The magnetic coupling between the primary coil and magnetic coupling between the primary coil and secondary coil increases, while the coupling with the other secondary coil decreases also. This results in difference in the magnitude of the induced voltage in the two secondary coils. The output voltage E0, which is the difference between ES1 and ES2, is therefore proportional to the magnitude of the core displacement from the null position. LVDT are highly versatile and used in wide range of applications where precise linear displacement measurement is required, including in some type of vibration pickups to measure the amplitude of vibration. Their non-contact operation, the core doesn't physically touch the coils, contributes to the reliability and long lifespan. Alright, we came to the end of our discussion on various types of transducers. Let's take a moment to quickly summarize the key takeaway from this video lecture. We begin by understanding why we need to measure vibrations. Also, we discussed the choice of vibration measuring instruments depends upon the several factors. The next, we defined a transducer as a device that transforms physical variables into electrical signals, and then delve deeper into variable resistance transducers using the strain gauge as a primary example, and then which is then using Wheatstone bridge, how to convert the strain into electrical signal. Moving on, we explored piezoelectric transducers which generate electrical charge and subsequently voltage when subjected to mechanical stress or deformation. Finally, we discussed electrodynamic transducers which operate on the principle of electromagnetic induction. I am concluded this video lecture with LVDT, a transducer that produces an output voltage proportional to the axial displacement of a core. This video provides a foundational understanding of some of the key types of transducers used to sense and measure vibrations. Each type has its own principles of operation, advantage and limitations, making them suitable for different applications and measurement requirements. Thank you for your attention during this lecture. In the subsequent sections, we will likely delve deeper into other aspects of vibration measurement and analysis.